Okay, thank you, cloud person in the data center. All right, so good morning. Welcome back. Hope you have had and are having a great week and happy Friday. The weekend is here, so that's a good or an impending. So that's always a good thing. So today, our purpose is to begin filling in formalism as it pertains to how we treat variables from a probabilistic and statistical standpoint. And we'll use these mathematical tools to frame our understanding of how we think of data, because that's going to help shape some of the methods and analyses that we're going to learn throughout the course of the semester. If you've taken stochastic computing with me, I think that was my first semester here, fall 2021. Some of this might be old talk. We're not going to treat it the same as we did then, but we'll certainly cover some of the same material. I curated on the course, I keep saying Moodle in my mind, course Canvas site, an open book. You can download the PDF, the URL is there, or you can browse it as a web page or at the website. And this particular text is covering material that I'm going to be discussing, but I'm going to use an approach that's a little bit different from the presentation of the book. But that's just to provide you a modality for books. You're welcome to view it electronically. You're also welcome to view it on the computer. I personally like paper. Let me put this forward. I don't know if I'm hearing it in this headset or if it's in the head. Okay, all right. So before we begin, the usual administrative bits. The reading has changed. And again, I don't test you on the reading. The deadline is there to help you with pacing so that you're staying on top of the material that we're going to be presenting, at least for the next week, week and a half. And so it's Intro to Probability for Data Science, and it's in the course resources section. I tried to name things with a schema to make it easier to find things that are books versus tools versus notes and other things like that. And so please take a look at that. I don't expect you to memorize everything in it, but that's to provide you a written form of the topics that I'll be discussing in our class modules. Project number one, this morning, I posted the solution, at least for the Python portion. I saw that you all handed it in. Great. Congratulations. Pat yourself on the back, do your happy dance and all that good stuff. Project number two, I'll be giving you an early peek. I'll be pushing it on the Canvas site this evening. I just have to get a bunch of other stuff done. But it won't be due until a week from this Tuesday, right? Please take a breather over the weekend. We will be doing visualization for project two. And on Wednesday's lab session, we'll be going over practical things for visualization, some of the visualization APIs in Python, specifically the Matplotlib library. And then we'll also be using something called Jupyter Notebooks, which is something similar, but not the same as a full-fledged development. Okay, any questions? No questions? So don't be alarmed like our squirrel up here. I'm a big fan of internet memes. So if you have some memes, send them my way and I'll put them up on the slides. Okay, so don't be alarmed. It's just for pacing. If you choose to look at things early, that's your choice. If you choose to take the weekend off, that's also perfectly fine and your choice as far as this class is concerned. All right, any questions? No questions? No? Still a little kind of sleepy? Yeah, I tried to stay up on the slot side, but I got to 6. All right, so it's interesting as a faculty member, especially when you're new to a university. A lot of people ask you a lot of questions, which I entertain, and certainly the usual questions about that. And there are some professional questions and some other, semi-personal questions. And so one student, I remember my first semester, asked me, do you wear the same thing every day? And I say, well, not really. I really do have 10 black moth turtlenecks and about 8 pairs of khakis. And it's been that way since high school. And I remember Steve Jobs, the late Steve Jobs, who was the co-founder of Apple, he adopted this uniform, right? And so in high school, I said, aha, that's what I'm going to do. And so for a long time, I have been in high school since a really long time ago. I've been wearing my black mock turtlenecks and khaki pants. You might see me with a blue shirt every once in a while. So no, I don't wear the same thing every day. Not that that matters. It just allows me to kind of focus on other stuff and not have to worry. I just go in the closet, pick that one, which is the same thing, and get the pants, and I'm good to go. All right. I'm not saying you should or you shouldn't do the same thing, but this just works for me, and I'll never change. This uniform, so to speak, Jobs got that from Izzy Minaki, Japanese designer, who introduced the idea of called sticky patch in industry, casual, but it's still a little bit sticky. And so that's where it comes from. I fear we're curious. So you can focus on data science and the black turtleneck. All right. So to jar your memory, when we last left off, we talked about file systems, and we used that discussion to motivate the abstraction of the blocks and the sectors and this way of storing bits and bytes through magnetic polarization. We have an abstraction rather, we talked about for our file system. And this was presented by the operating system, and is nothing more than a way to store files, but to aggregate sets of files under named structures, namely our directories. And in the early days of computing, you didn't have directories. And then they created directories, but they were fixed. And then that grew to you, an individual user, being able to create directories of your choosing. And this gave rise to a tree structure. And a tree is a really important data structure from computer science. It has a lot of applications in things like AI, as well as search, and all sorts of other types of applications. And so we then pivoted to the command line. And this command line is important, especially when you're building a processing pipeline. And we gave some examples from macOS, and I posted this morning a cheat sheet for command line function rate commands for the Windows command line this morning. It's on the move side. And we drove around to take a look at the file system structure, the directory structure on my laptop, but also use this to motivate our discussion about carriage return and line feed, how you terminate strings. Okay. Any questions about this? No? No questions? All right. So in everyday life, you're going to deal with uncertainty. And handling uncertainty and representing uncertainty in your data, in your measurements, is really, really important. Because at the end of the day, even though you're going to have this uncertainty, you're going to have to calculate and compute things from these insights you extract. And so if the underlying data can be uncertain, you need tools in order to reason about it, a calculus as it were. And that's the tools from probability and statistics. And so suppose you're dealing with a retail establishment, like a coffee shop. The notion of the number of customers that visits the shop and when, there's a seasonality to it. There might be a morning rush. There might be a lull in the middle of the day. There might be a rush of customers and increase dramatically in lunch hours. And then it might peter out in the afternoon. Now, if you are trying to extract insights from data and produce a report and communicate that, and the underlying data, how many customers, is uncertain, you need other stuff in order to extract those insights. And so this can impact lots of things for an enterprise, especially if you're using data-informed approaches in order to make your statements that you derive from insights you extract. You might use this information, the seasonality throughout the day or the week or the month or the year to determine things like how many employees should be working each shift. Because employee costs are the single largest expense for any enterprise, if you get it wrong, the revenue or money you're taking in might not be enough to support all your employees, and you might end up going out of business. And so this idea of representing these measurements, albeit uncertain measurements, is really, really important. And part of this class is we'll provide some treatment, not compared to what you have in a full semester in probability and statistics, but we'll provide some treatment that we need in order to use the tools that we have available to us to extract insights in spite of these uncertain measurements. Okay, any questions? No? All right. And so it all starts with this idea of systems that traffic in multiple outcomes. Whenever you have some system under study from which you're taking measurements, you have to describe what you see. But how do you do that if you have multiple outcomes or values for measurements that you get for your data? What are you going to do? Well, let's start with your casual understanding. So I'm going to get you talking at 9 something in the morning. What is an event? What's an event? We're going to don't call them some music.
It's like anything that happens.
Yeah. Anything that happens.
Yeah.
Yes, absolutely. Anything that happens. So suppose I flip a coin. Let's have a. Let's flip a coin. Let's just toss it out there. Not I mean. Just flip it out there. What happens? What did you see? Heads or tails? Tails. Some outcome. Okay. So let's flip it again. Let's have you flip the coin and just cut you out here. We just done. Tails again. Aha. You saw tails and then you saw tails. So that means when you flip a coin, it's always tails, right? Right? Yeah. But I just showed you that. That's not how it works. What's wrong here? Okay. But I just showed that to you. I'm trying to look for my clicker. There we go. So you flip a coin. You certainly know that it happened because you could see it. And you made an observation. We know observation is necessary in order to take your measurement, especially when the system under consideration is uncertain. Okay. So it's not just any measurement. It's all possible measurements. And like we saw with the coin, it's not enough just to flip it and say, well, it's always tails, and it doesn't always work out that way in class. But it's important to list out everything that is possible to be measured for your system under consideration. Now, this can be very simple for simple systems like the coin flip. It can be a little bit more complex for other systems. And so this event happened, something happened that occurred, and it resulted in something you saw. So we know measurement is a necessary part of uncertainty. Now, the question I asked, or the assumption I made, it was false, and I asked you what you saw. Well, we saw tails happen twice. And absolutely, everyone from a casual understanding knows that it's naive just to base my description of the system based on that very, very small number of measurements. Now, when we think of variables or columns in a CSV file, a variable is nothing more than a measurement. And one of the things we're going to do is relate it to the formula that we're going to call, or that is called a random variable. Okay. Any questions? Does that make sense? All right. And so, is it the same each time? No. Let's try this again. Okay, I'm going to flip the coin. This time it's heads. You're absolutely right. It's not the same each time. If it's not the same each time, let me ask you this. Then how do you describe it? How about you? You made a loaded word. What if we didn't know what probability was? Let's be more casual here. We're going to fill in some rigor. But since this is 125 and the prerequisite is just calculus and 120 or equivalent, it's not assumed that we have probability in this course. So how would you describe it?
You try it multiple times and write out the different outcomes.
Yes, you'd make an accounting of all of the outcomes. Okay, so you have to study the system in order to be able to write out all of those outcomes. Okay, now let's think about a different event, rolling a die. So let's have somebody over here. So let's go ahead and don't hit me, please. Just give it a roll. And what did it come out? 2. All right. So is this different from the coin toss event? How? It isn't? It is? Who says it isn't? Don't be shy. It isn't? Well, I'm going to say it isn't. Is it different from the point cloud system? It's different? Okay. So let's ask, let's think through this. How might it be the same? It's something that happens, yes.
It's both equally likely.
Equally likely outcomes. So y'all have a little bit of probability. You're absolutely right. And we haven't gotten into that, but you're absolutely correct. It's random, and we'll fill in what that definition means. All of the outcomes are equally likely. But we haven't yet defined this idea of equally likely. Excellent. Thank you for answering. How is it different? Let's think about that. Yes.
There are more possible outcomes.
Multiple possible outcomes. How does it compare to the coin flip system? How does that die roll compare? Die roll has 6. So in this system, we have, oh, where'd it go? Okay, right there. In this system, we have more possible outcomes that we can traffic in when we talk about this type of system, and therefore the measurements that we make from it, the observations. Okay. Any questions? No? All right. And so an event needs a number of ingredients. We need something to happen. More formally, this is called an experiment or a trial. We need an observation to be able to examine an outcome. And the important part, which alludes to what you were talking about when you said equiprobable outcomes, we need this idea of when can I see you again? Now, I don't know about you, but I think every answer in life can be related back to 80s R&B. And so a probability, this idea of how often a particular outcome can arise, is kind of like young love. When I didn't write, when will I see you? I want to see you again. But when you might be infrequently, see them. And this idea of a probability relates back to the numeracy. How often will I see a particular outcome among all the outcomes that I can measure for my system? Okay. So whether you flip a coin or roll a die, those are sort of casual examples. But what about something like taking a photograph? You get your digital camera or your cell phone or what have you, you snap a photograph. Well, you have some number of rows of pixels, some number of columns, and each pixel, each dot can take on one of a large number of different colors. And so every photograph that you could possibly take is a very complex measurements, a lot of moving parts, a lot of different measurements, but absolutely a particular picture is nothing more than a set of random variables, these measurements. Now, of course, if you have a large number of different possible choices that you can have for your pixels, it's going to be very infrequent, right? But what it means to be a particular type of picture, whether it's a picture of a dog versus a picture of a cat, it corresponds to this when can I see you again? Because certain choices of pixel colors in relation to one another are more frequent for certain types of photographs than others. So you can absolutely mechanically describe the content of images using this idea of when can I see you again? How often will they appear? And in the case of an image, together. Any questions about this? Does that make sense? Okay. So you're going to remember this song. All right. Anyways, so you observe an outcome, like the side of a coin, the side of a die roll, or a 2D matrix of pixels. And you don't know which outcome defines the experiment or the system under consideration. So you have to write out a collection of all of the possibilities for that particular system. So for the coin flip system, you enumerate them or list them out, heads and tails. Okay. For the die roll, 1, 2, 3, 4, 5, 6, you can do the same thing. It's quite a bit. And in practice, you wouldn't write them out explicitly, but you could do something similar for all the possible images that you can represent for a given resolution. And so mathematically, we use the framework of sets, to write out collections of things. And these have certain properties. Set is not necessarily ordered, and you will have at most one of each unique object in that set. Now, the nice thing about this is that you can count or you can enumerate the number of items that appear in the set. And this idea of counting is really important to describe this idea of when can I see you again. And so to make it a little bit more formal, there's a construct, omega, which is just a symbol used to denote this possibility of all, or the collection of all the possible outcomes that you can measure from a system. And this is called our sample space. And so I've taken sample space omega and I've added a subscript so that you kind of have an idea of what system I'm talking about for this enumeration or collection of all the possible measured outcomes. And so we have omega coin for coin flip, heads and tails. We have omega die for the die roll that has objects 1 through 6 representing the side of the die. A 10-year-old lives on these things, but I no longer. Okay. Any questions? That make sense? All right. And so in our omega, for those particular examples, I've listed out heads and tails and 1 through 6 for the coin system and the die system. But more generally, you just list out events and you number those events. And so here we have a generic sample space omega, and we have event 1, event 2, event 3, without loss of generality, meaning without any particular ordering implied. And we're going to take our sample space omega, our set of possible outcomes we can measure from our system under consideration, and we're going to put the set of natural numbers next to it. And now we're going to pair a one-to-one correspondence, each of our possible events in order with each element of the set of natural numbers. Now, natural numbers correspond to things you see in nature. I see 1 cow, I see 2 trees, I see 5 buildings. And if you look through the history of math, it's actually pretty interesting. The invention of zero is a human construct, and zero was intended to fix up flaws in this idea of numbers. Because if you said, how many cows do you have? I have 0 cows. You can't see 0 out in nature. You don't have any cows. I have 0 cows. You don't have any, right? So 0 is a human invention. And you'll see oftentimes throughout these constructs, there's this big oopsie, right? Oops, it broke. I have to fix it up. And 0 was one of those cases. In fact, 0 is considered at one point evil and dangerous because it doesn't correspond to the natural order. But anyways, the history is interesting. So we pair each one of the elements for our sample space, all the possible observables we can measure from our system under consideration. We pair it with one of the natural numbers. And sometimes, if we do that, we run out of measurables, our sample space. It's so-called finite. And if it's finite, you can certainly use this idea to measure the number of elements that we have in the set. So we pair this, that's called counting mathematically, pairing elements of your set with the naturals, 1 to 1, and we have a maximum. And in this case, this maximum is some natural number we're calling n. Okay. Any questions about this? Does that make sense? So now, this n, the stopping point for our counting, represents the cardinality or the number of elements in our set. And so in this case, the cardinality of sample space omega is n. We note this compactly, mathematically, with these vertical bars, meaning magnitude for the count, in this case, because omega is a set. And so here we say the cardinality of sample space omega is n. Okay. Any questions? Does that make sense? So why in the world did we do this? We did this because we want to know this question: when can I see you again? When can I see event 1, event 3, event 5 again? Each time I run an experiment or a trial and measure the outcome. Because this idea of when can I see you again corresponds to this idea of importance of those measurements. Okay, so if we know we have a cardinality of n. One of the questions, just brain hiccup, coffee's kicking in. Yes. So if we were to measure the cardinality of omega di, well, we know that we can count all of the sides. There are 6 many sides of a die. So the cardinality of omega di is going to be 6. Now, one of the things we can do is use this fact to describe the events in a much more complex system. The die roll has a cardinality of 6 for a single die roll, a sample space. And so if we were to express this, when can I see you again? If each side of the die is as likely as the others to occur, each of the sample space, you divide 1 by the cardinality of your sample space omega. Right? So that's going to be our proportion describing this, when can I see you again? When can I see the 4? 1 upon 6. When can I see the 5? 1 upon 6. Now, you might wonder, just like what happened with the coin flip, the first 2 flips came up tails and tails. When you define this proportion has to do with a large number of trials. So you run your system, run your trial, you make your measurement, do it again and again and again a large number of times, and this proportion is going to eventually equal this 1 over cardinality of sample space omega. Any questions? Does that make sense? Yeah, all right. So we have the simple case of a single die roll, and we can use this idea of our 1 upon cardinality of sample space to think about how many events we can observe for a more complex system, as well as calculate those proportions. When can I simulate it? So one question is, how many events do we have possible? What's the size of sample space omega for n big N many rolls of a die? So let's think about this. So you have n events, something happens, someone comes along, a big arm from the sky, just rolls some die n many times. And so we're going to draw a slot representing each roll 1, roll 2, roll 3, etc., to roll big N. And for each one of those rolls, there are 6 possible outcomes. Because we know for a single die roll, that cardinality of sample space omega is 6. So in this case, our something happens is more complex. And so if we take each one of these slots, for each roll, we have 6 many outcomes for roll 1, 6 many outcomes for roll 2, etc., up to and including roll number n. So now, if we list out each one of these outcomes, for each choice of roll 1, let's say roll 1 was a 2. I could roll 1 as a 2, and then for that roll 1 being 2, I fix that. And roll 2 could be 1, 2, 3, 4, or 5, or 6. So anytime that happens, it's going to be multiplicative, right? You multiply all these possibilities. And so that's 6 choices times 6 choices times 6 choices. That's 6 to the big N many outcomes for big N many rolls of the die. Does that make sense? Any questions about this? Okay. Now, these are just some of the schemes. There are many others that we'll talk about for how you enumerate the possibilities for your sample space omega for certain types of systems. And we'll introduce that when the time is right during the semester. Any questions about this? Does that make sense? Yeah. And so the reason for this multiplicative approach to counting all of the possibilities you can observe for our sample space omega, I'll illustrate here on the board, that's a note to me, with this tree expansion. So if I rolled a 3, for that first roll of a 3, my second roll could be 1, 2, 3, 4, 5, or 6. So I have for roll of 1, 6 possibilities. For roll of 2, for the first one, 6 possibilities for the second one. Roll of 3, 6 possibilities. And so if you tabulate together all of those outcomes, it multiplies. Any questions? Does that make sense? Yeah. All right. So if you were to compute the probability of a particular sequence of outcomes, 1 through 6 for each slot, the probability, again, would be 1 over the cardinality of the sample space. In this case, it would be 1 over 6 to the n. Any questions? Does that make sense? Okay. So let's continue on with this idea of events and probabilities. We said you need 3 ingredients. Something happens, that's your trial or your experiment. You need an observation, some type of measurement, and this when can I see you again? We have our cardinality that we use to tell us the numeracy of all of the possible outcomes for our system. I think I jumped ahead with this. And so we express the degree to which our event is probable. And so when we do this, that's our probability. Now, probabilities are expressed by the 100 per centum or through the 100. I took Latin for 5 years in grade school, and then I'm going to find a way to use it now as an adult. But nonetheless, the reason for expressing our probabilities as percentages is similar to what proportions do for increasing. If you said your portfolio increased from $100 to a value of 150, or another person said her portfolio increased from a value of 200 to 300, well, the second person, her portfolio increased by a larger amount. But you can't really make that comparison unless you register them on the same scale. So you say increase by 50%. And so for this reason, in order to make fair comparisons, you always traffic in percentages by the 100 per centum when you talk about probability, because these proportions represent how often across your large number of trials you're going to see a particular outcome for your measurement occur. Okay. Any questions? Does that make sense? Okay. And so we have our mega die, and we said there are 6 many outcomes, and we counted it. So the cardinality of a mega die is 6. Therefore, the percentage, the probability for any of those events from omega die is 1 upon 6, or 1/6. Same thing for the n many rolls of a die. Something happens, we have those n many rolls, and rolling n die at the same time is the same problem as rolling 1 die n many times. It's exactly the same problem. So something happens, we have those rolls. We make the observation that string of characters 1 through 6, n many characters long. And our proportion then is just 1 over the cardinality, or 1 upon 6 to the n power. Any questions? And so this particular type of system is a random system. And random, it has a specific definition. It means equiprobable. All of the possible observable outcomes will occur when you can see you again with the same proportion per centum. Any questions? Now, the opposite of random is stochastic. Now, if somebody says, I just had a random thought. I have a random thought, that's a stochastic thought. You can kind of teach your friend about it. If you have a random thought, that would be kind of weird. Pizza. Temperature, that would be a random thought. I can't even do it. But anyways, I digress. Any questions? Does that make sense? So going forward, we reserve the word random for equiprobable and stochastic for the dual of random, meaning that not equiprobable. Another word for not equiprobable is also bias. You have a preference for a particular outcome among the possible outcomes. And what that means is that the probabilities, when can I see you again, is not equal for your outcome. So if I were to present you with a so-called loaded die, I could do that and then take the material and put maybe a lead weight closer to one side so that that side is more likely to fall down. That is a stochastic system versus a fair die is random. Now, consequently, loaded die and gambling is against the law. So don't use a loaded die to gamble. Question?
Yeah, what's the formal definition of stochastic? Because I've heard it used as a random, having a random distribution. It makes sense.
Stochastic means changing. It comes from the Greek. I wish I learned Greek. We had to learn Latin hated it, didn't appreciate it. I wish I paid more attention. But to answer your question, who's changing it from? I think it's still Coast or something like that. I can't remember. Any other questions? No? I know Yasu, Tanamon Gary, right? I can introduce myself. That's okay. All right. Any other questions? No? All right. Makes sense? All right. So let's turn our discussion, and this is going faster than I had planned because I was expecting more questions. Let's turn our discussion to random variables. Now, what a random variable does is it introduces this idea of arbitrary measurements or functions that you compute over what we're going to call the raw observation. We talked about observables from systems like Einstein as well as a die roll. You can imagine, say, flipping a coin some number of times. One thing you might want to ask yourself is not what is the probability of a particular sequence of heads and tails. You might want to compute the probability that the number of heads, for example, is equal to k over 2, and let's assume you had an even number of coin flips, big N. Does that make sense, the setup here? And so this function now allows you to relate data to arbitrary measurements, because data is nothing more than a measurement about something. And introducing this framework of arbitrary functions over our observation allows you to cause computational things to our system of probabilities. Okay. And so we have some function, and in this notation, let's imagine an individual event, whether it's something like a sequence of heads and tails for flipping a coin and many times. It could be an image from a camera, a pixel array. So let's call omega our quote unquote raw event. And in this case, our raw event is a sequence of heads and tails and many slots wide. And now we have some function over this raw event. And so this idea of a random variable is a function, and that function is evaluated over a raw event, and it returns some value. And so this framework, when can I see you again? We're going to now introduce a framework for how you get from the base event to this measurement over the raw event. Okay. So here we have our coin flip, and you can imagine any kind of function. Let's say you're measuring something like temperature. A useful function for temperature might be the first derivative, the rate of change. For heart rate, might be this idea of the average. So in this framework, there are all sorts of functions that you can invent over your raw events. So here, with a function, you have your domain, and domain is, you can think of inputs to your function. And collectively, all of the possible inputs to your function, that's called your domain, right? It's what the function is evaluated on. And associated with this function for each input is outputs of value. And if you collect together all of the possible outputs that function can make, that collection is another set that we call our range. So we start out, we instantiate some event, that's our observable, that's our raw event or our base level event. We evaluate our function on it, and we get some value, namely an element of our range. Now, this range can be a lot of things. It can be the set of naturals, it can be a set of real numbers, a set of rationals, it can be a set of integers, it can be all sorts of things. It doesn't matter what it is, but what matters is how you take this measurement over the base event from our domain and calculate this idea of when can I see you again, that proportion. Okay. Any questions? That makes sense? All right. So when you talk about the random variable, what you're talking about is the value that is determined as a result of measuring this function. Okay, now I'm just depicting that generally as f of omega, and I use lowercase Greek omega, symbol omega, to denote the event, where uppercase omega, that is the sample space. Any questions? Make sense? All right. And so the range on this thing is only up to here. Keep trying to run back. Okay. So let's go through this calculation. So let X be a random variable measuring the number of heads. And we're going to assume for this example, for pedantic reasons, that we're going to flip 3 fair coins, right? Fair is a synonym for random, meaning the outcomes of sample space omega coin equals heads, tails. That's going to be uniform or fair or random, equiprobable outcomes. And so armed with that, let's imagine then we flip this coin 3 times, or we take 3 coins and flip them. We have a string of heads and tails of size 3. So here, if we take our random variable, in this case, our random variable is to measure the number of heads. So it's going to iterate through that string, we're going to implement it, and every time you see heads, it's going to increment the counter. All right. So here, we're going to look at all the possible values that our random variable, this function, the number of heads, can take on. So if you flip a coin 3 times, we could either have 0 heads, we could have 1 heads, we can have 2 heads, or we can have 3 heads. So the set 0, 1, 2, 3, that's going to be our range that we talked about on the right-hand side. And so with this, we say the probability of 3 tails is the probability of having tails, tails, tails in that sequence. So what do? We'll say, okay, well, what is the probability of getting single tails on a flip? It's random, and we know the cardinality is 2 for omega coin. So the probability for a single coin flip is what? 1 over 2, 4.5. So we know the first tails has a probability of 0.5. The second tails also has a probability of 0.5. The third tails has a probability of 0.5. So that's 1/2 times 1/2 times 1/2 is 1/8. Okay, or 0.125. Okay. Any questions about that? Does that make sense? Now, when we list out this next scenario, the probability that our function, our random variable, returns a value of 1, well, there are different ways we can get a single heads in this flip that's 3, many 1. We can get a heads in the first position, a heads in the second position, or heads in the third position. Okay. So each one of those has to be accounted for, because here we're talking about the random variable equals 1, not the probability of a particular string or sequence heads, tails, tails. Okay. And so there, again, we say 1/2 for heads times 1/2 for tails times 1/2 for tails. And we can have a 1/8 for this expression, 1/8 for this expression, plus 1/8 for that expression. So that's 3/8. Any questions about this? Does that make sense? So we do that for probability of having 2 heads, right? That's heads, heads, tails, heads, tails, heads, tails, heads, heads. Again, that's 1/8 plus 1/8 plus 1/8. And then lastly, the probability of having 3 heads that return 3 from a random variable is a probability of heads times heads times heads, which is just 1/8. Question.
How is the probability of having 1 head the same?
It's how is it? Because the positioning is the same amount. Because you have heads in the first position, heads in the second, heads in the third. Here, because you only have 1 tail, so you can think of this alternatively as having tails in the first position, tails in the second position, or tails in the third. Okay. Thank you for asking the question. Does that make sense? Question.
What did you say the probability?
1/8. Because the probability of getting the first flip of the head is 1/2 times 1/2 times 1/2. So 1/2 times 1/2 times 1/2 is 1/8. Or 1 over 2 to the 3 power, or 1.
And then for the 2, it would be.
This is 1/2 times 1/2 times 1/2. Plus 1/2 times 1/2 times 1/2. So it's 1/8 plus 1/8 plus 1/8, which is 3/8. Because when you have this string, you're multiplying, just like we did in this example. So in the case of the coin flip, we have 3 slots. So we have flip 1, flip 2, flip 3. So here, flip 1, that can either be heads or or tails, all right? For each one of these choices, that could either be heads or tails. For each one of these choices, that can either be heads or tails. And if we were to count all the possible outcomes, there would be 8 of these paths from our first flip to the third. And so for each choice, you have 2 choices here. In any of these choices for the first flip, there are 2 for the second. And then for any of these here, there are 2 for them. So you multiply 2 times 2 times 2. But the probability is 1 over 2. 1 over 2, 1 over 2. Does that make sense? But the probability of a heads is 1/2. The probability of a tails is 1. So we are looking for heads. And here, the random variables measure the number of heads. We enumerate all the different ways to get 2 heads here. But the probability of a heads outcome for a fair coin is always 1/2 for heads and 1/2 for tails. Question.
Can you also just submit it if there's 8 combinations?
Yes, you could absolutely look that way. But in this exposition, I'm trying to relate and many points from that previous one, but absolutely we do it that way. Any other questions? No? Make sense? All right. So now we'll fill in our probabilities for our random variable. Now remember, this is for the random variable. We have the probability of getting 0 heads is 1/8. The probability of getting 1 heads is 3/8. Probability of getting 2 heads is 3/8. And lastly, the probability of getting 3 heads is 1/8. Okay. So now we're gonna do an accounting of this random variable's outcomes. And here in this table, we list the random variable in the first column, and we have the probability on the second column on the right. Now, in this notation, I have the probability of big X, a random variable, equals little x. And in the literature, the style is whenever you refer to the random variable, you use the uppercase alpha character. And whenever you refer to the value that it takes on or returns, you depict that using the lowercase alpha. And so here it refers to the probability that random variable big X takes on value little x. Does that make sense? All right, any questions? So here we have the outcome taking on 0, 1, 2, 3 is probability 1/8, 3/8, 3/8, and 1/8. And you notice here, if you add them up, it totals 1. Now, this idea of totaling to 1 is a law that governs what it means to be a probability, so-called law of total probability. If you take the probability of every possible outcome for a system and you add up those probabilities, it must equal 1 in order for it to be a valid probability. Any questions on this? Understand? No? All right. So now we can list out all the outcomes and we can compute the probabilities by evaluating the outcomes that our random variable, this function on our base event, can take on. And we use all of our first principles about the cardinality of the sample space for the simple events to calculate these more complex quantities. All right. And so this table is a complete accounting of all the values the random variable can take on and the associated probabilities of potential. And so this is the so-called distribution of a random variable. And that distribution is a collection of probabilities associated with a random variable, and it's complete. So all the values of your distribution, for it to be a valid probability, must sum to 1. Okay. Any questions? Does that make sense? Yeah. All right. And so notationally, we can write out this probability in functional form, and you'll often see it as P of X, where little x is the value that it takes on. For random variables, you talk about the probability of its value. And so that's the equivalent of saying the probability that random variable or measurement big X takes on the value little x. And so this is often called, for countable quantities, the so-called probability mass function, or PMF. And the reason it's called the mass function is because you can think of these probabilities as a weight or a mass. And I'll kind of talk a little bit more about that in another setting. And this distribution effectively tells you how the mass is spread out. It's almost like you're making like a peanut butter sandwich, right? You put the bread down and you spread the peanut butter. Sometimes the peanut butter is really thick. That's a bigger mass or bigger probability. Sometimes the peanut butter is really thin. That's a smaller mass and therefore a smaller probability. And so what this distribution does is it tells you how this probability mass is spread out over all of the values in the range for the random value. Any questions? Does that make sense? And so in alternate considerations, sometimes the probability is thought of as a so-called importance weight. And it's called importance weight because the idea is that values that are quote unquote more important are going to occur more frequently, right? If the system says this matters to you, it's going to show it to you more often across your large number of trials. Okay, so we take this probability and listing out a table for something like the number of heads for 3 coin flips. Well, that's pretty easy to think about, but it's not always so straightforward, particularly as the number or the cardinality of the sample space gets very, very large. Moreover, there are some sample spaces that are countably infinite and some sample spaces whose infinite or infiniteness or infinity is so big that you can't enumerate them uncountably infinite. And so we need a little bit better framework instead of always writing it out in a table. It's very useful to visualize it. So here on the horizontal axis, I have all of the outcomes for random variable big X. And along the vertical axis, I have the probabilities. And so for X is 0, we have probability 1/8. For X is 1, we have probability 3/8. For X is 2, we have 3/8. And for X takes on value 3, we have 1/8. And so these are sometimes called the mass points because it's a probability mass function. It's taking this probability mass and spreading it out over all of the values for the range of this random variable. Sometimes this horizontal axis is called the support set for the probability, right? So those are synonyms, the range of the random variable or the support set for the probability. But nonetheless, these mass points are spread out or distributed in some fashion over our support set. Okay. And so if you draw the envelope by graphing these mass points, note the shape of this graph. And the shape then becomes a proxy for how thinly or thickly spread out across the support set our probability mass function places these probabilities. And so it's so important that we can kind of ignore the individual mass points and just look at the shape. We know that at the extremes, 0 and 3, this 3 coin flip system, it has a smaller probability. And in the middle, for 1 heads or 2 heads, we have a larger probability mass. So if you were to wager on this system, you would be more likely to be successful if you chose an outcome in the middle here, because it has higher probability than if you chose the outcome at the extremes. So important is the shape of this distribution as well, that when you're trying to discuss the behavior of the system, there are lots of summaries that you can do, and we'll talk about those summaries that describe the shape of the distribution by its graph. And so we'll absolutely talk about this idea of moments and what they do and how it relates to the shape of this probability distribution. All right. Any questions about this? Does that make sense? Yeah. All right. And so the distribution, and more correctly, its shape, describes something, at least in information retrieval, called the aboutness of the data, of the data. What values occur and what is their relative frequency? Because that describes completely the shape, how this system behaves. And you can do all sorts of things with this. And it's better to do this descriptor of shape for your distribution because it's not always practical to list out a table for it. And sometimes it's not even possible. Any questions? Does that make sense? And so this idea of characterizing the shape is achieved through what in this class we're going to call probabilistic averages. And let's introduce this by playing a game. So, does anyone want to gamble? I'll promise you I'll give you a money back. All right. So why don't we have you come up? That's right up, honorable operator. Okay. So if you have $1, I'm going to put $2 on the table. And you can put $1 on the table. Today in class, we learned how to gamble. But don't go to Foxwood. Dr. Holmes didn't tell you to go to Foxwood and figure out probabilities. They don't look fine. There's nothing illegal about it. But I didn't tell you to go to Foxwood and you probabilities. You have a puncher? Whoa. I don't really know that one is okay. Well, let's continue to go. Wow. Oh my gosh. Well, that defeats my whole thing, but you didn't know. So suppose, and what's your name again? Alan.
Yeah.
So let's imagine. Where's my clicker? All right, here we go. Alan, we're going to gamble. And let's imagine you wager $1. Well, I like this game more than my game, but you wagered $1 and I wagered $2. And I'm going to flip a coin. And before I flip a coin, you're going to guess the side. So guess your side. Heads or tails? Okay, tails for this. Whoa! So when you guess that outcome, you can have okay. I like that game more than my game, but you guess heads or tails. I flip the coin, and it's a fair coin, right? There's a problem if it's a biased coin, right? Because that means heads and tails are not going to be 50% probability each. If you're correct, you get to keep my $2. If I'm correct, I get to keep your $1, or in this case, your $100. But nonetheless, let's imagine you're correct, you keep my $2. I'm correct, I keep your $1. Now, one of the questions you might want to ask is how much will you win or lose if you keep playing this game? Now, when you talk about winning, okay, that's a function that returns 2, positive 2. If you lose, the money you quote unquote get is -1, right? So what is very helpful for us is one of our probabilistic averages that we'll talk about, and many others, is this idea of the center of the distribution for the expectation. And so half the time, probability of heads is going to be 0.5, and your money function is going to be a value of 2. And then the other half the time, probability of tails is 0.5, you get -$1. So we'll compute a probabilistic average, and we'll say 0.5 for the win case. You're going to get $2, so 50% of the time, you get $2. And then the other 50% of the time, you get -$1. Okay. So if we compute this, that ends up being 50 cents. So if you try this game again and again and again and again, you're going to be ahead on average 50 cents. Now, of course, if you wager $100, I could plug this in and I make out really, really well. Now, certainly when you design games of chance, the casinos explicitly designing games in their favor, right? You might get lucky and win something here and there, but they always end up on top, right? So this idea of a probabilistic average is a way of summarizing the aboutness of your data so that you don't have to traffic in tables for your distributions. You don't traffic necessarily in graphs. You're trafficking in the so-called shape of the distribution. And this idea of the probabilistic average is in general the framework you use to calculate aspects of shape for your distribution, because it's the shape that tells you the behavior of the system in a nice compact fashion now we have the tools to deal with situations for very complex systems or very, very simple systems. Any questions about this? Does that make sense? Thank you for volunteering. Okay, so different probabilistic averages describe how stochasticity behaves for a particular system. And we'll talk about different probabilistic averages and what their purpose is in describing the gross level behavior of your data generating system. And so we'll do that on Monday. Stay tuned. Same place on Monday. So I will see you then. Have a great weekend. Oops. And I trip over that every single time. And I will, the solution for the Python for the project one is already on the Canvas site. So let me stop the recording.